Let's go ahead and look at a few more examples. So if we have 10x to the negative 3 power plus 5x to the negative 4 minus 8x, and when we go ahead and take the derivative, we're using both the power rule and our constant multiple rule. So our 10 is going to be multiplied by the derivative of x to the negative 3, which is negative 3x to the negative 4, because remember we subtract 1 from the exponent. We have plus 5 times negative 4x to the negative 5, again subtracting 1 from the exponent, and minus 8x. Remember, when we subtract 1 from x to the 1, it becomes x to the 0. X to the 0 is 1, and 1 times anything is 1. When we go ahead and combine these, I have negative 30x to the negative 4 minus 20x to the negative 5 minus 8. Let's go ahead and look at number 4. Now, number 4, we're given functions that are fractions. So if f of t is equal to 7 divided by t minus 5 divided by t cubed. And the best way to go ahead and deal with something like this is rewrite the function in terms of exponents, whether they're positive or negative. And so when we rewrite this function, we have f of t is equal to 7t to the negative 1, because t is in the denominator, minus 5t to the negative cube, again because that t cubed is in the denominator. When we go ahead and take the derivative, this negative 1 from here is going to come to the front, leaving us with negative 7. Subtract 1 from the exponent, we have t to the negative 2. And again, we're going to go ahead, we have a minus 5 t to the negative 3, the negative on the 5 and the negative to the 3 change to a positive. 3 times 5 is 15, and we'll subtract 1 from the exponent. We have t to the negative 4, and we always want to return it to the way that we found it. So we have negative 7 over t squared plus 15 t to the 4th power. Let's look at the next example. So we have negative 2 divided by the cube root of x. And again, you want to go ahead and rewrite these in terms of exponents. So we have negative 2x to the negative 1/3 power. The derivative means we got to go ahead and take this piece, go ahead and divide it here. So we have 2 times negative 1/3. And we have to subtract 1 from the exponent. So we're subtracting from 1 divided by 3. We're subtracting 1 or 3 divided by 3, which is going to give us x to the negative 4 over 3. Go ahead and combine our exponents. So we have a negative and a negative here on our constants, which gives us a positive. And 2 times 1 is 2 divided by 3. And then we have x to the negative 4 divided by 3. And we always want to go ahead and make our exponent positive. So we have 2 divided by 3, and our x to the negative 4 over 3 comes to the bottom here. It's not necessary to go ahead and make that into some sort of radical. All right, so let's look at another one. So here we have a function x cubed minus 5 divided by x. And first of all, we want to go ahead and simplify f of x by dividing by x and go ahead and writing as exponents. So x cubed divided by x is x squared, and 5 divided by x is just 5 over x, which is also x to the negative 1 power. And so once we get that, we can go ahead and take the derivative piece by piece. So derivative of x squared is 2x to the first, or just 2x. And minus 5, be a minus coming from the negative 1 here, x to the negative 2. And then from there we can go ahead and rewrite it again with positive exponents. So we have 2x minus 5 divided by x squared. And sometimes we have things like d over dx, d to the x in parentheses. Just we want to go ahead and find the derivative without necessarily writing function notation. We just want to go ahead and differentiate. Now differentiate meaning is going ahead and finding the derivative. And we don't always necessarily want to use function notation, although always that would usually be the best practice. So here we go ahead and use our d subscript x notation to find the derivative. And we want to find the derivative of 9x to the negative 1/2 plus 2x divided by x to the 3/2. And we want to go ahead again and write our exponents, whether they're in the denominator or numerator, we want to go ahead and write them out. And then we want to go ahead and differentiate. So we're going to have 9 times negative 1/2. And then if we subtract 1 from negative 1/2, we end up with negative 3/2. And we're going to add to that because of our signs. We're going to go ahead and add 2 times negative 3/2. Eventually this is going to become negative x to the negative 5/2. And then we're going to write our exponents as positive values as we write our final answer. So we have negative 9 divided by 2, x to the 3 divided by 2. We don't need to write that as a radical. Minus 3, x to the 5/2 divided by that. And again, we don't need to necessarily write that as a radical. So let's go ahead and look at some problems where this might be useful. So we want to go ahead and find the slope of the tangent line to the graph of the function. And we have a function of y is equal to x to the 4th minus 5x cubed plus 2 at x is equal to 2. Well, in order to go ahead, we want to find the tangent line, we need to go ahead and take the derivative. And we can go ahead and use our power rule here. So we have 4x cubed and then minus, now the 3 times the 5 from the exponent is going to be 15x squared. And then we have a go ahead and find our derivative. And then at this point, we need to go ahead and plug in x is equal to 2. So when the derivative is equal to 2, we have 4 times 2 cubed minus 15, 2 squared. And we go ahead and simplify that. 2 cubed is 8. 8 times 4 is 32. 2 squared is 4. 4 times 15 is 60. So we have 32 minus 60, which is negative 28. Now, in order to go ahead and finish this out, we need to find a y value for the x that we're given in the original function. So in the original function, if we go ahead and plug in 2, we end up with 2 to the 4th minus 5 times 2 cubed plus 2, which is 16 minus 40 plus 2, which is equal to negative 22. And now we have a slope given from our derivative, and now we have a point given by our value of x and the y value that we found. We can go ahead and plug it into our point intercept form. So we have y plus 22, because remember the formula is minus, so we have to go ahead and change it to a plus. Our negative 28 is from our slope of our tangent line, times x minus 2. 2 would be given from our problem. And if we go ahead and simplify this, put it in point slope form, we have y is equal to negative 28x plus 34. Let's go ahead and look at another problem. So right now, for number 9, we want to find all the values of x where the tangent line is horizontal. And when a tangent line is horizontal, that means the slope is equal to 0. So we have a problem f of x is equal to 2x cubed plus 9x squared minus 60x plus 4. And the first thing we need to do, because we're finding the tangent line, is we need to go ahead and find the derivative. So if we go ahead and take the derivative using the power rule, we have 6x squared plus 18x minus 60. Now, the derivative represents the slope of the tangent line, and so therefore we need to go ahead and evaluate it at certain values. Now, we know the slope of a horizontal line is equal to 0. And so we want to take the derivative and set it equal to 0 and solve for x to find out what that particular value is. So when we go ahead and take our derivative value and set it equal to 0, we can go ahead and factor out a 6 to make our life just a little easier because it's a GCF. And we end up with 6 times parentheses x squared plus 3x minus 10 close parentheses. And therefore, we're only really evaluating what's in parentheses for this value. So when we go ahead and plug this in, x squared plus 3x minus 10 factors, and we end up with 6 times parentheses x plus 5 close parentheses, open parentheses, x minus 2 close parentheses equal to 0. And now 6 is never going to be equal to 0, so we cancel that constant out. And when we go ahead and solve this, we have x plus 5 is equal to 0, or x is equal to negative 5, or x minus 2 is equal to 0, and therefore x is equal to 2. So therefore, our answers for x are equal to negative 5 and negative 2. Let's go ahead and look at an application problem based off of this concept. So here we have a revenue, and we're assuming a demand equation is given by Q is equal to 5,000 minus 100p. We want to find the marginal revenue for the following production levels, which is the values of Q. And we want to go ahead and solve the demand equation for P and use RQ is equal to P over Q. And we're going to use 1,000 units, 2,500 units, and 3,000 units. So let's go ahead and take this equation and solve it for P. So if we have Q is equal to 5,000 minus 100p, we got to go ahead and subtract 5,000 from both sides. And we have Q minus 5,000 is equal to negative 100p. Go ahead and divide by negative 100, and we have negative 1 over 100q plus 50, because 5,000 divided by 100 is 50, is equal to p. And then we want to go ahead and say, okay, RQ is equal to P of Q, and so our P is negative 1 over 100p, or P over 100, however you would like to write it, plus 50 times P, and because we are multiplying P times Q and we solved Q for P, and therefore R of Q is equal to negative P squared divided by 100, or negative 100 times P squared, plus 50P. And our marginal revenue is the derivative of all of this. So our derivative over this is negative 2 divided by 100p to the first power, which simplifies to negative 1 over 50p, plus 50, and that's not going to change as we go through our simplification process. So if we want to go ahead and plug in 1,000, so our derivative with 1,000, and we go ahead and plug those values in, we end up with a value of 30. If we go ahead and plug in 2,500, we find out that the value is actually 0. That's not actually a bad thing. It's not negative, so we're totally okay with that value. And then if we plug in 3,000, we end up with negative 10. Now, if this were a real life situation, we would find out that something is dropping and we're losing money. But we just were asked to plug in values and get results.